Welcome back. This will be now a new topic called computer systems. So this is brand new in isolation. So if you didn't do two on the previous one, the previous topic on number systems, representing data, well, this is brand new. Have a new stab at this one. We're going to do part lesson on truth tables and then the second part of the lesson in another video on logic diagrams. Let's crack on. You're going to find out about the different logic gates in this lesson, and do some simple truth tables for those and for the simple logic circuits, the result, and interpret the result of those. And then the next lesson after that will be about logic circuit diagram. Did you know about logic gates, voltage, microprocessors, hardware, software, a logic statement, truth table? So let's tell you about all of those things. How are logic gates and circuits used? Well, hardware, do you remember what hardware is? There's hardware and software. Software is the thing behind the screen, the stuff you can't touch. Your apps, your word processing software, your web browsers. Hardware is the physical stuff that you can touch, the things like a keyboard, the screens. Well, all of those things which are digital have processors in there, or very simple processes, circuits in there, and those are all made up of logic gates. What is a logic gate? Well, it's the actual foundation of every digital circuit. You assemble one or more logic gates to make a digital circuit, and this then will control the flow of all the electronic signals that go through the circuit, depending if something is on or off. Now, as soon as I start saying on or off, you can start thinking, oh, on or off, that's the 1 and 0 stuff. Good, you should be thinking along those lines. So one or more inputs will flow into a gate, and only one output will come out of the logic gate. That logic gate will behave differently depending on what those inputs are. So the logic gate will not control the inputs go in, the logic gate evaluates those inputs and then makes a decision of what the output will be. So key term for you, logic gate, the part of a digital circuit that controls the flow of electronic signals or electrical signals through the circuit. Moving on. We'll talk about voltages. Why are we talking about voltages? Why are we talking about voltages being high or low? Well, if you think about the on-off states, the high or low states, if the voltage is high, you could represent that in binary with a digit of 1. So what's low going to be? Yes, 0. So some of the circuits are very simple, just add a few gates. Other ones use much more complex structures called microprocessors, which will require thousands of logic gates. So microprocessor, key term, an integrated circuit that has similar functions to a central processing unit in a computer. It's just much simpler. Voltage, just in case you don't know what that is, potential difference across an electrical component. The potential difference across an electrical component. I don't know why I'm speaking South African, but we'll carry on. How are logic gates and circuits used? Different logic gates have different outputs. All depends what input it gets. There's 3 of them you need to know about. ANDs, ORs, and NOTs. AND gate. For this one, use that symbol there, bit bullet shaped. It's got 2 inputs, 1 output. You label the inputs and the outputs, in this case it's A, B and X. AND gates always have 2 inputs, always have 1 output. If we look at that diagram, you can have a logic statement to represent that. And you kind of work backwards here, so get my mouse pointer out. You're kind of going backwards. You're going to say that X is made up of A and B. That's what it looks like. X equals A and B. So it's almost backwards. You're going to say there's going to be an output X, and that's based on the A and the B inputs being ANDed together. You could use a full stop, which they use in A level, to show it, but at GCSE, just stick with the words AND. What's a logic statement? It's a statement that's declared to be true or false. Moving on. What is the logic of an AND gate? It's very simple. If you want the output X to be 1, both A and B need to be 1. So to sum up an AND gate, all inputs need to be 1 for the output to be 1. If any of those inputs is not a 1, X is always going to be a 0. And you can think about ones and zeros as being true or false. So you can think of as 1 being true and 0 being false. I also think about it as multiplication. And that explains a bit more if we use something called a truth table. Now what that is a table that just breaks down the logic of the circuit by listing all the possible values that could be used. Key term, truth table, a table that shows the breakdown of logic by listing every possible outcome. Well, how do you know you've got every possible outcome? Count up in binary. Look. You've got the input here. These are the columns. It's got two inputs, A and B. Look up here in the corner. There's your two inputs, A and B, going through an AND gate and then coming out of it with an X. So there's your output X. So A and B. Now let's count up in binary here, just for these first two columns. Using 2 bits, if you remember that, they were 2 digits. 0 using 2 bits is 0 and 0. Then count up in binary as 1, which is 0, 1. Then go to 2, which in binary is a 1 and a 0. And then 3, 1, 1. You can't go up to 4 because you've only got two columns. So you'd have 1, 0, 0. So that's how you always never miss an input. If you had 3 different inputs and you wanted to test every possible outcome, use 3 bits and start counting up from 0. 0, 0, 0. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, blah, 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 and then you're done. So, reading this, how I remember ands is I think of multiplication. I think of anything multiplied by 0 is 0. So you can remember this if you want by going, if the input is 0 and the other input is 0, then the output will be 0. But if you think in the terms of multiplication, nothing times nothing is nothing. Nothing times 1 is nothing. 1 times nothing, again, is nothing. And 1 times 1 is 1. So you can try and remember that exactly as it is there, or just think of multiplication. So remember, the only time you saw a 1 there was when everything was a 1. And a quick note, if you have 2 inputs, you have 4 possible outcomes. You know this because you just use 2 bits, 2 digits. 0, 1, 2, 3. 4 different rows, 4 possible outcomes. And like I said, remember true, you could think of true as 1 and false as 0. Look in your GCSE question. If it's got the truth table as F, F instead of 0, 0, they're meaning false, false. So give your answer as F. For goodness sake, if they say F, F and then you write down 0, that's not what they want. They want you to use what they're using. So if it's zeros they're using, use zeros. If it's ones, use ones. If it's Fs or Ts, use Fs or Ts. Got it? Right, let's move on to OR gate. That looks like a similar shape, though it's curved in round here, and it's curved a little bit more. It's not as flat, not as blunt. If we go back one, remember it's like a bullet shape, straight down, and then a curve, whereas you'll see the OR gate much more pointed and curved in here, and that's the OR gate. Again, you label the inputs, label the outputs. This OR gate, any OR gate, will have 2 inputs and only 1 output. So like the AND, which always has 2 inputs and 1 output, the OR always has 2 inputs and 1 output. What does the logic statement look like? X is going to be A or B. So X is going to be A or B. At A level, they might use the plus symbol, and that'll give you a little clue about how you try and remember how this is evaluated. But just stick to OR. Let's look at the truth table. Again, covering all the possible outcomes, starting from 0 and just keep going up until you run out of digits. And I think of OR as addition. Nothing plus nothing is nothing. Nothing plus 1 is 1. 1 plus nothing is 1. And 1 plus 1 is 2. Oh, well, there's no 2 in binary, is there? So just think of it as 1 and 1 is 1. It's true. So true and true. So add these together, right? And multiplication or adding together. And as you can see there, as long as there's a 1 in any of the inputs, the whole thing is going to be a 1. And again, there's 4 possible outcomes. Last gate then is the NOT gate. Looks a bit like a triangle with a circle on the end of it. And there only is one input and one output, and it's just reversing it. And so that's a little bit different. Labeled very similar to before. The output's X, the input's A. What does the logic statement look like? X is not A. In GCSE, just use the word not. Don't use any weird symbols like you would use at A level. Let's look at the truth table for that. Only as one input, so only one column, and you start at 0 and you go up to 1. It's very simple. If it's not 0, and you've only got a 0, 1, if it's not 0, it can only be the other thing. So it's not 0, it's 1. If it's not 1, it's 0. That's it. It's probably the simplest of all the gates. Just think opposites. And remember, only one column, so there's only really two possible outcomes. So have a look at these. Have a look at my notes. Have a go at filling in the blanks. I'll pause the video, well, you pause the video, and we'll come back in a second. Alright, so let's start with this one, which is the AND. Count up in binary. 0, 0. What's binary for 1? Using 2 bits. It's 0, 1. And remember, is like multiplication. Nothing times nothing is nothing. Nothing times 1 is nothing. Now going up in binary again. 0, 1. 2 using 2 bits is a 1 and a 0. Multiply those together. 1 times 0 is 0. And then 1 times 1 is 1. Go down to the OR here. Think about addition. Nothing plus 1 is 1. 1 plus nothing is 1. This one requires you to count up in binary. So 0, 1, 2. So this must be 3, which is a 1 and a 1. And then addition, 1 and 1 is 2, but we can't have 2 in binary, so just think of it as 1. And that's that one. Final one. If the input is 0, and you want to do the opposite, what's the opposite to 0? 1. Now if you're counting up using 1 bit, it's 0, the next one would be 1. And you can tell anyway, not 1 is 0. It's as simple as that. Off you go. Edmodo. Quiz there, required to look at some pictures. Called Computer Systems Logic Gates. Off you go. And assuming you've done that, well, we're done with this part of the lesson. Next one requires you to do logic circuit diagrams, but in this lesson you should have learned about not and or logic gates. They're part of most hardware, if not all hardware. They're the fundamental building blocks of circuits. They control electronic or electric signals throughout the circuit. And you should be able to interpret how truth tables work. Cheers. Bye-bye.